The stator core of an AC motor is an iron cylinder made up of hundreds of layers of laminations packed tightly together. The laminations form slots running along the length of the stator core into which coils of insulated copper wire or strands known as windings are inserted. When energized, the windings form a magnetic field which the stator contains and conducts, while also controlling the electrical field distribution. The winding coils are evenly spaced out around the stator in pairs. Each pair is 120 degrees from the previous one. The 120 degrees is significant as this is the separation of the three phases in the AC main supply. When we apply each of the three phases to its corresponding coil pair, the generated magnetic fields will also be 120 degrees out of phase. As a result, a rotating magnetic flux is generated, will travel around the stator. If we place the electromagnet we made earlier into the stator and apply power, its magnetic field interacts with that of the stator, and it starts to rotate. Add a shaft, and we have an AC motor. Now, this motor design, known as a synchronous motor as the rotor rotates at the same speed as the flux, doesn't need a commutator like the DC motor did, but it still needs the rotor to provide an active magnetic field, either with a DC-powered electromagnet like in our example, or with permanent magnets. Synchronous motors have advantages and are used to great effect in certain industrial applications. But there is another kind of AC motor that's even simpler. We saw before that if a conductor is moving in a magnetic field, then a voltage is formed by induction. When a pair of parallel conductors, like the rotor of our DC motor, is placed in the stator, the rotating magnetic flux will induce a voltage, which in turn makes a current flow within the conductors. This current will in turn create its own magnetic field that will interact with that of the stator and cause motion. Of course, this current is only induced while the rotor is moving relative to the rotating field, which means it can only happen while the rotor is turning more slowly than the stator field. Luckily, though, the rotor is slowed by the load it's driving, as well as by friction and other losses, so it's always turning slower. The difference between the speed the stator field rotates and the actual speed the rotor turns is called slip. And when slip is involved, the motor is said to be an asynchronous motor. So we have a usable torque without needing to apply power to the rotor. The needed current has been induced. We have created an induction motor. Most modern industrial induction motors use rotors with a number of parallel conductors arranged to form a cylinder. With a ring at each and joining the conductors together, the rotor forms a sort of cage, which gave rise to the name Squirrel Cage. Modern motors also use additional sets of windings to increase the number of poles from the 2 in our motor to 4, 6, or more, making for a more uniform magnetic field. Increasing the number of poles also lowers the speed of the motor, with the rotor speed halving each time you double the number of poles. Although induction motors can be coupled directly to the mains and run at a fixed speed based on the mains frequency, the motor speed can be accurately controlled and efficiently optimized by powering the motor with a variable speed drive, and we'll look at the importance of the efficiency in more detail in the module.